Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. How are you? So, before we start the course, please do the presents first. Then, well, let me start the course with the following presentation. So, okay, today we will discuss about elementary graph algorithms. Actually, last week I explained that we will discuss about the combination of dynamic and greedy algorithms and, well, and others also. For example, with complete search and then divide and conquer also. But I think it's more interesting if we integrate or if we combine to solve the problem of graph with the approach of dynamic programming, etc., which will be discussed next week. Actually, we have started with the greedy because last week we have discussed about graph in greedy sort of spread problem which can be solved with which can be solved with greedy. It means with Dijkstra, but for others also like minimum spanning tree, etc. So that's only small example of solving algorithm in graph with for paradigm. And today we will start to discuss specifically about graph. Okay, let me get computer. So today we will discuss about elementary graph algorithms. Mainly we will discuss about DFS and BFS. Then we will discuss, we will try with basic example. This is the reference. Mainly I take some courses of Mr. Subakti. Then I take several categories of graph traversal problem categorization in from Halim and Felix Halim and Stephen Halim, competitive programming 3. Well, mainly for the detail itself, the elementary graph algorithms, the details comes from Introduction to Algorithm, Corman et al. So it's mainly as the base of this course main root, you can see like that. And then for others also, and of course, I took a lot of sources from data structure courses. So maybe some courses over here is just like a repetition of my courses in data structure. But well, we'll make a differences between data structure, and design and analysis of algorithm, of course. And last, we will discuss about the problem provided in here, provided in the Alex Toki, as usual. So here, what's the interesting part about graph? This is one of the implementation of graph, and by the meaning of graph itself, the vertex or the vertices are people. In this case, when we talk about social media, we can see or we can measure the distance between one person to another person. So, and in this case, an average of all, each person in the world, at least among 1.59 billion people active on Facebook. So it uses data on Facebook is connected to every other person by an average of 3.5 other person. Actually, exactly, it's like 3.57 other person. What does it mean? It means that from me and, for example, the president, Mr. Jokowi, in average, well, for me, you and others, in average, we have a connection with maybe Mr. Jokowi or even Mark Zuckerberg. We have average like 3.57 point. It means that I know person A, and person A know person B know person C, maybe person C know person D, and then person D know Mark Zuckerberg. So that's the distance. And it's very interesting, and in terms of research, it's widely used. So it's important to understand graph. Even for the practical, it's widely used, and well, it's demanding. Well, previously, before social media start to explode, previously there is a term like six degree of separation. What does it mean? It means that something like this: everyone is on average 6 steps away from any other person on Earth. So, for example, you and Bill Gates, it's on average it's 6 steps away from any other person on Earth. Well, this research is from 1969, which is this is the when the Apollo reached the moon. It's very interesting because at that moment, without the advancement of internet, well, without the advancement of technology like today, but Stanley Milgram can decided or can conduct research about the 6 degree of separation. Actually, the first context over here is for the games. It means, well, for in the games, but further researchers can prove that it's applied also for our reality. Well, it's still widely used also today for the real world case, not the social media. And this is called 6 degree of separation. That's graph also, absolutely. Then that's why it's important and study the graph. And this is we start with the definition. Maybe in data structure we start talking about graph starting with 3. Well, it means that I think you have to be well understood about the 3. Therefore, we can directly discuss. This is the reminder, like the definition graph is data structure that consists of a set of nodes and a set of edges that relate to nodes to one another. Vertex, this is the like terminology. The vertex is a node in a graph, a dot in a graph, something like this. This one. Edge is in the line or pair of vertices representing a connection between 2 nodes in a graph. So it's a line over here. And we have a term, there is a term also about undirected graph and directed graph. Well, undirected graph, it's like this. There is no row, or we can Tahiti, Honolulu, and Honolulu and Tahiti, it's the same thing. While in directed graph, it's like Honolulu and Tahiti, and it doesn't mean that Tahiti Tahiti and Honolulu is the same thing. For example, this one, A and B, but not B and A. Not from A to B, okay, but it doesn't mean like B to A, because it's different. So this is, well, this is the basic definition. You will find a graph in everywhere in your daily activities. This is the route distance between cities, or distance, well, like the distance flight distance, and this is the method in chemistry, and this is message transmission, and this is tree, binary tree for exactly specifically. And this is, like I explained last week, this is the formal definition of a graph: vertices and edges, a set of vertices and edges. Furthermore, this is the example how, given a representation of graph, how we can write it in formal definition. We can write it like this. For example, vertices of graph 1 is, well, is a set of A, B, C, and D. A, B, C, and D. And the edge is AB, AB, AD, BC, BD. It's, well, like combination, AD and DA, it's the same thing. But normally we put, well, because it has no rank, if there is no rank, or if there is any rank or order, like A, B, C, normally, it's easier to put the smallest, the first, like something like this. But actually, there is no rule for that. And graph 2 is directed graph, so it has to be declared clearly, especially in the edges. So 1, 3, and 3, 1, 5, 7, 5, 9, 9, 11, 9, 11, 9, 9, and 11, 1. And this is 3. And this is because graph 1 is undirected graph. The order of vertices in each edge is unimportant. So it's like combination. Where if the diagram is dgraph, directed graph, it's and the abbreviation of directed graph, graph 2 and graph 3. Direction of the edge is indicated by which vertex is listed first. So like G and D over here, G and D and D and G, it has different meaning. Well, this is others. First kind of undirected graph. We have connected, path cycle, disconnected, and tree. And for directed graph, we have directed cycle, strongly connected, weakly connected. Well, we will discuss terminology one by one. Not all in general. Well, we'll discuss a lot of theoretical foundation for this one. And we start with this one. Given this graph, undirected graph and connected. So there is a term called adjacent vertices. What does it mean? It means that two vertices in a graph that are connected by an edge. For example, this one, 4 and 1. It's the adjacent vertices of 4 is 1, 2, and 3. And, well, sorry, this is not the correct representation. This is the degree, actually. Let me put this one, I think. This one. Let me make it undirected. So I delete the graph. Okay. So for example, we return the vertex E. What is the adjacent vertices of vertex E? The adjacent vertices are D, C, F, and G. That's the adjacent vertices. While the degree of a vertex, what does it mean? It means that it's the number of adjacent vertices. For example, for E, there are 4. For A, there are 2, B and D, respectively. Well, And for B, there are 2 also. For D, there are 3, A, F, and E, etc. And if we do the sum of all the edges, of all the degree, the sum is 2 multiplied by the number of edges. For example, in here there are 1, 2, 3, 4, 5, 6, 7, 8. It will be 16 adjacent vertices, or 16 degree of vertex, because adjacent vertices each count the adjoining edge. So we count this one and this one. That's why we multiplied by 2. This is degree of vertex. Next, previously I give you the image of path. What does it mean? Path is a sequence of vertices that connects 2 nodes in a graph. For example, connecting from Surabaya to Lamongan. From Surabaya to Lamongan, we have a node Gresik, because we can go from Surabaya, Gresik, Lamongan. Or maybe we will have another route like Surabaya, Mojokerto, Lamongan, or Surabaya, Mojokerto, Bojonegoro, maybe Tuban and Lamongan, return, etc. So this is a path, a sequence of vertices that connects 2 nodes in the graph. Simple paths, A, D, F, E, G, something like this. And this is simple path. While cyclic or cyclic path or cycle, actually it's a simple path, except that the last vertex is the same as the first vertex. It means that we start with A, we have to end with A. Yes, we start with A, we have to end with A. This is important when you have to understand traveling salesman problem, or another problem which needs to be returning to the initial point, or for the expedition. For example, you have one truck and you have to deliver within the cities. For example, the truck is in Juanda, and you want to deliver it in Kaputi, maybe in Tunjungan, etc. Another point, several points in Surabaya. So you have to decide the route or the path, and you have to return. Of course, you have to return the truck to the Surabaya, to the warehouse in Surabaya and in Juanda. That's why it's widely used. Well, this one normally when you do on the Google Map, when you want to find out maybe where is the closest market, or closest maybe you want to buy something, some product. And Google will recommend you with the shortest path, like something like this. But normally in Google it's another story, because it's a heuristic approach. It's not the really global optimal, but it's more like approximation, because the complexity of the problem. But in simple way, it's simple path. Another graph terminology, there is a connected graph. Any 2 vertices are connected by some paths. It means that all given a graph, all vertices are connected between each other. It means that well, let me take an example for this one. For A and G, we have to pass D and E. For example, for A and F, we can do A, D, F, or we can do A, B, C, E, F, depends on the weight, maybe. So it's connected on. Well, disconnected. There's connected, and of course there's a disconnected. Disconnected means that there is a vertex or subgraph which is not connected with another, and we call this this one subgraph. Well, we have to define firstly about subgraph, subset of vertices and edges forming a graph. It means that actually when we see this one, and we take an example of 1, 2, and 3, this is subgraph of graph of this graph. Or 1 and 2, only 1 and 2, it's the subgraph or this graph. But in the case of disconnected, the subgraph, it means, well, it may be like it consists of several vertices, or maybe it consists of only one vertex. Connected component. What is connected component? In the simple way, it's the maximal connected of subgraph. So, well, this is the further explanation. What does it mean? It means that how many subgraph or how many separated, well, how many separated graph, separated subgraph given certain graph. For example, for this graph, graph G, it has two connected components, which is this one. This is the first subgraph. This is the second subgraph. So we can see V, A, B, C, D, and G. And E we declare all, and G has two connected components, which is the first one. Well, with this one, the first connected component is A, B, C, and D, which is connected, and C2 is E, F, and G. Actually, this is important when you have a problem for finding a connected component letter. Seems simple, right? And then we have tree. Well, I don't need to explain about tree because you have already familiar with this one, and we have discussed and we have well, we have a lot of discussion about tree, etc. And forest. Forest is collection of tree. Where does this term is important or is widely used? One of the used term of forest. Well, forest can be well, it consists of several trees, two or more trees. And in certain cases, like in machine learning, maybe you know the term of random forest. Well, it consists of several tree model. A model that can be, well, for each tree, it's like a model which can be expressed as a tree, especially normally in like a binary tree. And there are several different tree combined together. That's why it's called random forest, and other contexts also. Well, it's later for artificial intelligence or computational intelligence. We can continue this one. Complete graph. Complete graph is a graph in which every vertex is directly connected to every other vertex. For example, this one, A is connected to B, C, and D, as well as B, C, and D also. And this one also. For this one, this is complete directed graph, and this one is complete undirected graph. And while for a weighted graph is a graph in which each edge carries a value. It means that from C and D, sorry, yes, well, you can do this. C and D, there is a weight or there is a value. And it's easily like when we see the map, this is this example distance of Austin and Dallas, and between Denver and Chicago, Washington, Atlanta, Houston, etc. So this is the cities in USA. This is the weight. Others, well, others, this one. We have, well, vertices node, okay. Weighted or unweighted, okay. But self and loop, not yet. Directed acyclic graph, not yet. We have edges, undirected cyclic, okay. Multiple edges. Well, we will discuss later through the example. Tree forest, okay. Sparse isolated multigraph Eulerian, not yet. Then reachable is it means that from the connected component. Simple graph and bipartite, okay, not yet. In out degree, connected subgraph complete. So some of them we have discussed. And for further, we have we'll discuss, for example, directed acyclic graph. We will discuss next week, and etc. Actually, I would like to propose you a sub problem that we encountered during our research, our current research about graph. So, well, I will post the problem next week, and whoever get the answer correctly, optimally, I will I will give you a reward. for solving the problem. And how we represent the graph? Actually, mainly we have two only: adjacency list and adjacency matrix. But I put the first one at least it's listed in the course of Mr. Subakti. So, and I think it's interesting to show you what's the representation. We start with the edge list. This one. This one is easy to implement. So, for example, you have linked list over here. For each linked list, you have two value. So actually, in the point, there are 2 points maybe. There are 3 pointer maybe over here. The first pointer is for the next, or the first pointer is for this the point A, and second pointer is for point B, and the third pointer is for the next list. But finding the edges incident on a given vertex is inefficient, since it requires examining the entire edge sequence. So we have to examine all of them. It means that if we want to find the optimal value of, for example, GFK to Mia, we have to see, well, maybe there is no relation. Oh, yes, there is a relation, GFK Mia over here. We have to read all of the list for the worst case. That's why it's inefficient. While this one is a little bit more efficient, and it's easy to understand maybe for us, which is familiar with iterative programming or structural programming. So it's easy to understand. Adjacency matrix. So we can represent a graph with adjacency matrix. This one is undirected graph. It's easy, right? Like A and B over here, or A and B over here. It's the same thing. So we have to consider only half of them in order to optimize the computation time. 1, 2, 3, 4, 5, 6. Actually, okay. I forgot to color it. So 1, 2, 3, 4, 5, 6. Okay. This is a graph is represented in the form of two-dimensional array. The size of array is V multiplied by V, where V is the set of vertices. Actually, this one is a good representation, but the drawback is you have to specify the amount of the size of array is the size of the number of the vertices power 2, or this one multiplied by this one. So maybe for small cases, or for like 1,000 for like 1,000 vertices, it's fine, because the size will be 1,000 multiplied by 1,000, and it will be there is a 1 million storage needed. But what if 100,000, etc.? Well, it will be a problem for you. And this is for the directed graph. I think it's easier, and we can solve the problem directly, as you can see over here. Well, we have to allocate it this one, but actually we only use this one, and it's faster. For example, if you want to find the connection between city 1 as well as this one also, city B and C, you only need to focus on this one. That's when the time as well as this one, the time complexity is the time this one, the number of vertices plus the number of edges, the worst case. That's the worst case. And last one, there is adjacency list. This is we use the term of actually A, B, C, D, E, F over here is connected. Well, this is a normal. There is another pointer connected this one. A graph is represented as an array of linked lists. The index of the array represents a vertex, and each element is in its linked list represent the vertices that form an edge with the vertex. It means that actually when you create an adjacency list, graph representation with adjacency list, you have to make a linked list well, in this struct, you have to make a linked list which consists of one value at least, which is the name of the city, or maybe the number of the city ID. Then the second value is next. No, the second you have to define pointer, which is maybe next or left or right. Well, up to you. Next, which refer to this one A, B, C, D, E, F, etc. Then we have to consider also like this one. So maybe the child or the connection is B. And this one we have the connection of D, etc. Actually, it refer to here, and then we continue again. It refer to D over here. And at the end, we put it as null, as usual, in a linked list. Or I think it's easier to see this example. So in this case, we have two value over here, vertex 0, 1, 2, 3, for example. So we don't need to save, we don't need to save the value over here, 0, 1, 2, 3, but it's based on the order and based on the iteration. We start with this one. This is like we refer to this one, and the first value is refer to the first value is the pointer, refer to the name of the vertex, and then the second value refer to the next. And the complexity time, it's similar to the adjacency matrix, which is the number which is the number of vertex, so the vertices, plus maximum number, or worst case is the number of edges. And this is others, like the combination. As you can see over here, this is the use matrix. There is array, and then it refers to several linked lists. While in this one is adjacency set and adjacency table. So this is like a representation, like for 0, given this directed graph, 0 set is 1 and 2, 2 and 3, 1 for 3 is 0, 1, and 2. And we can represent in adjacency table like something like this. So similar to matrix, actually. And this is the differences because mainly there are two adjacency matrix and adjacency list. So this is the differences. For the storage space, as you can see, adjacency list is more efficient in terms of the storage space. So the total number of vertices plus the total number of edges. While in adjacency matrix over here is the quadratic of the number of vertices. And in the case of adding a vertex, actually this one is quite complicated. Yeah. In order to add a new vertex to V and V, matrix in the storage must be increased to V. This is the absolute value plus 1. To achieve this, we need to copy the whole matrix. Therefore, the complexity is big O vertex, new value of vertex powered by 2. So in the case, because in this case, it uses array, static array. In order to, if you want to add another vertex, you have to create another array, then copy and paste all the value from the previous matrix or array to the new array. While in this one, because it's used a pointer and it's dynamic, it's only put next not null, but next is the new index, then set as null. That's all. The complexity time is big O 1. For adding the edge, it's directly. Directly, we can do directly something like this. For this one also can be inserted directly, so we can insert the this one. We can insert directly over here, so we can refer this one, we can insert this one, or you can put over here as the next. So For example, this one, if we put it at the end, we have to revisit at least in the long of the number of the edges. But in the best case, you can do something like this. You refer this to the new allocation, the new list, and then the next list refer to this one. So that's why it's big O, 1. Removing your vertex is you need to reboot again, for example, and this one, remove vertex, we need to search for the vertex which will require big O, V, and the complexity is V plus E. And removing, well, this one is quite the positive part of adjacency matrix. For removing an edge, you have to only need to put the matrix EJ equal to 0 or equal to maximum or infinity, for example. Well, this one you have to traverse. Yes, through the edge is required, and in worst case, we need to traverse through all the edges. So big OE. For a query, in order to find an existing edge, the content of matrix need to be checked. So it has an advantage for adjacency matrix, which is we can do directly refer to this matrix. For example, AAB, is it connected? So we can do directly A matrix and the address of A and the B directly, pick O1. Well, in adjacency list, we have to find one by one over here at least. We have to find, for example, A and B is over here, so we have to visit. Is it connected to this one? So we have to check this one. Oh, it's not connected. We have to check next. Oh, not connected. We have to check next. Oh, this one is connected. So it's connected. To find out it's connected or not, it needs a big OV. Okay, I think that's all. Before I start, well, because it's afternoon, it's time for sleeping. Maybe I don't want to give you a full tale about graph. I want to ask about you. I'll give you like 5 minutes. Give an example in your daily activities which use or which can be represented as a graph. You can put it in the comment in the chat box. I'll give you like 5 minutes. Well, whenever you find out the result, just type it. Starting from now. It has to be different with other person, so you have to be very fast. Actually, just okay. Google Maps, Avivilla. Okay, so okay, good Avivilla, Google Maps. So Google Maps or mapping couldn't be used anymore, or you have to use with different case study maybe. Well, maybe you can answer it right now. And I will mark it to show that you are attending this course. Maybe you have to well, you know that you have to put a comment in the chat. So if not, there is no comment from you, it means that you are not here. Organization structure, that's good. Yes, it's 3 normally. And rooms in my house. Yes, distance. It's it's a coloring problem actually. It's a very interesting problem. Domino brick, yes, it is. 5, 6, and 6. Okay, Dewangga. Yes, of course, Putu. It's computer network. And that's good. Okay. Yes, electrical circuit, it counts. So between resistor and transistors, switch, etc., it can be represented in the graph. Okay, others? Okay, yes, Vitra. Yes. Shopping at the market. What does it mean, Thomas? Najwa, shortcut path is already discussed in, well, it's included in Google Maps, so you have to provide another example. Thomas, what does it mean? Yeah, with the shopping. Toll system? Yes. Well, it's route. Family tree? Okay. Yeah. Back navigation. So I think with maybe cholesterol levels. Husnan, can you explain it to us? What does it mean? Farhan, transportation has already mentioned in flight navigation, train, and toll system, etc. Husnan, maybe you can explain what does it mean by cholesterol level? Well, I'm not familiar with this case. Yes, item recommendation in commerce, yes, it can be represented in graph. Connected water pipe in underground, yes. Supply chain, yes, it's for delivery, etc. I think like for shopping at the market, it's like you have to buy one product to another product, etc. And the tendency is like you put after you put milk, it's better you put cereal, because when people buy cereal, they prefer or normally they tend to buy milk also. That's a recommendation and can be represented in graph. Food chain. Mm, yes, it's graph, but it's not clear. Husnan, I'm interested in. Are you there? I'm interested in cholesterol levels. Well, you can explain it in bahasa. You look for another. Okay. Decision tree, yes. Determine the outcome of chess game. Yes, it's similar to decision tree also. Novel, what do you mean by traffic light? Red, green, red, yellow, green. Maybe you can elaborate or explain it. Pac-Man game, yes. Actually, Pac-Man game is like a deep first tree, deep first search. Sorry, deep first search. Yes, neural network. That's why deep learning consists of this molecules. Yeah, solving a maze. Yes, absolutely. Web navigation. It's already in. Okay, yeah, it's graph, right, and menu, etc. Blockchain is the graph. It's decentralized system. It applies maybe like in the context of the distributed For the blockchain graph, maybe it's more like computer networks, Clifton. Gene and genomes relation in, yeah, it's bioinformatics. Okay. That's all for others. Let me check how many students. Rail and road navigation. Zilda, it's already, it has been mentioned. Animal evolution, yes, it's graph. Well, yes, it's a directed graph. So actually, until now, there are 31, 31 plus at least genome 32, 33. Okay, okay, that's all. Okay, at least everyone just give the comments. Okay, thank you. So based on the chat box that you have sent to, based on your opinion or your comments in the chat box, we can see that there are a lot of applications of graph. And actually, how to solve that? And we start with the how to traverse, or how we explore the graph. That's why there is a term called graph traversal. Well, graph traversal is the way you traverse or you explore the graph. Sorry. Mainly, we have depth first traversal or depth first search, for searching, and the breadth first traversal. For depth first is a graph or roughly analogous to pre-ordered traversal of an ordered tree. So it's something like this. So you replace you remodel the graph into a tree and find it by one based on the depth first. Well, in breadth first traversal, well, this one is like a vertical approach, and breadth first traversal is horizontal approach. You have already. Well, these two, I think you have already familiar. And then after that, we have like, actually it's not, oh, sorry, it's minus graph gr. Actually, it's not only find, well, for traverse, mainly there are two, DFS and BFS for depth first search and breadth first search. But in the extended version or in the extended problem, there are several categories based on the Seven and Felix Salim. Well, it's mainly categorized in the problem of competitive programming. The first one is finding connected components, or well, there is a just normal traversal, then followed by finding connected components, mainly in undirected graph. And float fill, labeling, coloring the connected components, like you when you it's like when you color you see in the map of the world, like for each country we can how many maximum color we can represent it, so that like for one vertex with this neighbor, it's not it doesn't have the same color. Or for example, like we color Indonesia in red. How many color we can do so that other countries that has the distance with Indonesia, for example, Timor-Leste, Malaysia, and Singapore, it has different color. Or in Papua New Guinea, it has different color. So based on this one, actually based on Indonesia, we can decided that this is the maximum is 4 if we don't consider the sea, actually. But if we consider the sea, it's we need 5 color. There is a research for this one. Well, you can Google it. It's easy and it's old. It's old method. Coloring graph is widely used in competitive programming, and there is a topological sort where we have to discuss directed acyclic graph and inverted graph check, graph edges property check via DFS spanning tree, and finding articulation points and bridge, undirected graph, and finding strongly connected components, directed graph. Well, I have a research with Mr. Siddiqui about water pipe underground, and it's funded. Actually, if you are interested, next week, well, as I said previously, next week I will show you a problem, the actual real problem, and if you are interested, you can join. You will be a research assistant. There is a and well, there is some facilities for you. But let us see next week. Actually, it's in the domain between this one, directed acyclic graph, or this one, articulation point. And so we start with the standard, which is BFS and DFS. Maybe just for reminder or revisit or refresh your memory. Breadth first search, BFS, refers a connected component of a graph, and in doing so, defines a spanning tree with several useful properties. It's undirected graph G. It's like wandering in a labyrinth with a string. So it's like a problem in maze labyrinth. Starting vertex S is assigned a distance 0. Then in the first round, the string is unrolled, the length of 1 edge, and all of the edges that are only 1 edge away from the anchor are visited. So it's like a maze. The next word, which is this one, is 1 edge away, are visited or discovered. And then we continue growing. Maybe we can. It's easier to do this one. This is the example of the of using BFS, and actually in data structure application of BFS, you can use a queue to store the roots or to store this one. So, well, in DFS, it's mainly used like stack, and while in BFS, it use queue. For example, this one, Austin, we want to, we want to take all distance or all nearest distance from Austin. So we have Dallas. So we compare this one, well, Houston, Dallas. As you can see, we start with Austin. It's there are Dallas and Houston. Dallas is put in the front because it's maybe it's smaller, and followed by Houston. Okay. Then after that, actually, it's not considered the distance or the weight, I think. Well, the weight is only for the order. Then Houston, once Dallas, once we arrive in Dallas, we can go to Denver. Yes, I think Denver, Chicago, is it? Yes, and Chicago. Yeah, sorry. So Chicago and Denver, put it in the list. I think, yeah, well, it's not, the weight, it's not considered in this case. So it's only PFS. Chicago and Denver, and then Houston, the Q. Then we have what we have? We have Atlanta. So we have Atlanta over here. And then after that, we have Washington. we visit Chicago. Actually, Chicago, there is Denver. It's already mentioned over here. But in this case, well, this is the difficulties or this is the problem of BFS. Denver is mentioned over here from Chicago. Previously from Dallas, it's Denver over here, but then from Chicago, Denver is mentioned over here. So it's stored again in the queue. So after that, Denver, Atlanta go to Washington. Actually, when we arrive in Denver, we have to put Atlanta again over here. This is for using queue with BFS. Actually, I want to jump to this case. This is the problem in the BFS. Actually, Denver is in the queue twice, as well as Atlanta over here, as you can see. So what's the strategy in BFS? The first strategy is to mark it only after it's dequeued. So we mark it only when it's already dequeued. The second technique is to mark the city as having been visited before. It is put into queue. So we put the label or a flag over here. Oh, this one Denver is visited, so we don't need to consider Denver again. So put over here. So that's the strategy in BFS. Let us go up again. And this is another example of BFS based on the book of Corman. This is BFS on undirected. Let me know if you have any question or it's not clear before I forgot to explain to you. As you can see, this one is there is undirected and unweighted. We start with S over here as 0, and then we have R, and actually this one is W. Oh, okay, this one, sorry. Yeah, R and W. And then after we arrive at R and W, we start with V. It depends where we start first. In this case, it starts first with W. So we start with T and X. So R, T, and X. After that, we start with the weight 1, which is R. W, T, X, and T, X, and V. And then we move on to the next degree or to the next deep. This one XV T, we visit T, and then we have U over here. As you can see, this one is Q. We start the head is this one, the tail is this one. You add the last one at the end. So first in, first out. U, and then that's all. It's finding all the solution. So at the end, it's only find Y, and then when the Q is empty or null, then it stops. That's BFS. In terms of running time, this one, vertices are enqueued if their color the color is white, and in the queuing, and Q and the Q takes big O1 time, and total cost of this operation is big OV. Just to make sure that you have already marked or reflect the V. It essentially is vertex cannot the vertex Q. Sublength of all list is big OE. Actually, well, this one is theta E. Consequently, big OE time is spent on scanning all of them. So we have to scan, because we have to scan all of them, and we have to consider all the vertices. So the computation time is actually, well, it's not all of them. Actually, we don't need to consider this 1, 2, 3, but in the worst case, we have to consider all of the edge, and we don't need to return it again. So the total running time is big O V vertices, the number of vertex, plus edge, linear in the size of adjacency list representation of G. So in linear time, in terms of size of adjacency list representation of G. And here, reachable from source vertex X, it computes the shortest distance to all reachable vertices. So if you remember Dijkstra, it applies BFS for searching, well, for traverse the graph. Then it considers the weight. So that's why non-negative, the weight, I consider the weight, and it's only select the shortest at current time. For example, in this case, we compare Dallas and Houston. So Dallas, and then we compare it again, Denver, Chicago, or Houston. So smallest is Houston. Sorry, this one is first is Houston. Sorry, we select first is Houston. Then we compare it Houston, Atlanta, and Dallas. So we select Dallas. Dallas, we compare it between Chicago, Denver, Denver and Atlanta, or Atlanta over here. So I think the smallest is Denver. So if we visit Denver, sorry, it's not Atlanta yet. Denver, then we compare this one is 104,000, etc. So we measure all of them, and then we can find the optimal solution with Dijkstra. So it's PFS. This is the breadth first tree that can be built like this one. The formal definition of this graph that which is built from PFS. Graph this one tree consists of vertices reachable from S, and that's all. Well, this is one sample of the algorithm. Actually, you can find it, so it's widely spreading on the internet, so you can find it directly. The problem is not actually the problem is not build the BFS algorithm, but given certain problem, how you can adapt this problem, or how you can adapt this input in, which can be solved using BFS or existing code of BFS. That's the challenge. Okay, I think okay, that's for BFS. Before we start this one, I'd like to ask you to solve this problem. Yes, this is we use BFS, and well, it use greedy also, but in this case, because the weight it is a one, it's not it. It's more like complete search. Well, actually, can we use DFS? Yes, we can. But one of the optimal solution, I think I prefer using PFS. Well, you can start right now. I'll give you like 30 minutes to finish it all, because it's the difficulty over here is how to process this input. For algorithm of BFS, actually you can use maybe, let's say, BFS gigs. BFS in, well, this one in C++. Maybe you can apply this thing. But actually, if you use this one, it's not optimal. My suggestion or my advice is try to use only normal array, and then just take a distance from this one, visit, and this one, this one, this one. So rounding this one. By doing this, we will find the shortest path. Okay. Then see you in 30 minutes. And for you, if you have already, maybe if you have already solved this problem, well, I would like to ask you to, whenever you are already finished this problem, just put a comment in the chat box. Okay. Is there any question from for BFS maybe? No? Then good luck. See you in 30 minutes. Or whenever you have a question, just open your mic. I'm standby. So, okay, I think it's a little bit difficult to solve it in 30 minutes to submit it. As I see that in the submission page, there is still no one try to solve, to submit something. Okay, maybe, well, because our time is limited, maybe, well, I don't need, well, for now, I don't need to ask you for submit it right now. Just maybe if you, maybe can you share to us, maybe some of you, is there any barrier maybe to explain how you will solve this problem, how you solve the maze problem? Is there any barrier want to explain? Okay, Dewanga, DFS is used, it will recursively search every direction. PFS, okay. Okay, left, right, we up, down, okay. Yeah. On different works, if it hits the wall, it stop and refuse to be part of the plan, okay. And then they found the door. Okay, yes, and shortly, it means you use the movement of like LRUD, left, right, up and down. Isn't it, Dewanga? So, in terms of the standard library, which standard library you use for solving this problem? Do you use, for example, I think, for example, it's only we can use it only array, or we have to use it with dynamic representation. Well, for me, well, I correct my word previously. I use array to save the map, but for solving or for make a queue, I use queue and pair for the x and y. Maybe you have any suggestion? Okay, Dewanga, at least I put the point for you. Maybe is there any other comment? Let me know. Not yet. There is no comment. Well, if there is no comment, then we can discuss to the next case, which is DFS. This one, yes, still there is no filter. Yes. So actually, well, just for your advice, you can do the search from this one. Well, like what Dewanga did, up, down, left, and right. Then you try to figure out whether this one is a wall or a root. If a root, maybe the distance you plus plus, it's like you set it as plus plus iterated. So over here it will be like this, like this. Well, of course, if not, if for example this one is blocked, you can pass to the next one. But well, the easiest way is to like this until you find out the shortest route. Or maybe if you are interested using using DFS, it's fine. You can use like this one, then return back and backtrack again, and then this one maybe this one backtrack this one. It's up to you. Is there any comment before I continue, or maybe is there any suggestion? So it will be useful for you and your friend. It's correct or not? No? Or do you understand the problem? Let me know. Please raise your hand if you don't understand the problem. I'm happy to explain it again. So, everyone understand the problem? Okay. Yes, Rosa. Actually, I use Q for the solution. Well, it's the nature of, actually, it's I use the nature of BFS. Let us try to find out BFS over here. When you are looking for the source code of BFS on the internet, you'll find out, for example, this one, gigs for gigs. So as I explained over here, it's easier. Explained over here, it's easier to use Q for BFS due to its natural behavior. For example, this one, like let us see. For example, Austin, and then so we use Q to save this one, and the relation is Houston and Dallas. Houston and Dallas. And then the next relation after Dallas, we have Chicago and Washington. Chicago. Oh, sorry, not Washington. Chicago and Denver. So I try to move it into 3. And from Houston, we have Atlanta. Chicago, okay. Denver, in Denver, we have Atlanta also, okay. Then Atlanta, we have Washington. So this is the 3 representation. For this one. Therefore, how we visit one or how we search or how we traverse one by one. Firstly, we start with the starting point, which is Austin. Is it the correct answer? No. Then we move on to the next one. So we save it into, why it's save it into Q? Because we save it like this. After Austin, there are how many? There are Dallas and Houston. So Dallas and Houston. So we save it in queue. Let's say we save it in queue. Then after that we start with it's up to you whatever you want to choose. Whether you want to choose Houston first for the shortest problem, well for Dijkstra maybe, or you use Dallas maybe. That's as in this example it uses Dallas first, then use Dallas. Then as you can see, Dallas over here, it has 2 child, which are Chicago and Denver. So we save Houston for Let me do the representation. Well, Austin, we start with Austin. Then we have, okay, then after we visit, we pop out, we pop or the queue and enqueue the new instance for Dallas, Houston. Let's say this is the first in, first out. Okay, then once we select Dallas, we pop or we dequeue Dallas. But in this case, before we dequeue Dallas, we have to insert well the new Houston. We have maybe Chicago and Denver over here. But Dallas already pop up. It's dequeue. Oh, sorry. X. Control V. No. Yes, this one. Houston. Then after that, we visit, we check again Houston. For example, this one, Houston, it has Atlanta. Then we put Atlanta. We enqueue Atlanta for the queue. Well, in here there is still Chicago, Denver and Chicago. And we dequeue the Houston. So it will be like this. After that, well, actually, in real case, it's like you move the queue, but it's automatically because you use standard library. So you can use a standard library include queue directly. Then after that, we visit Denver, and Denver. Okay, we visit Chicago. Chicago, it's already Denver, but we have already marked it. We have to mark it that as it has been visited. So at the end, until Atlanta, once we arrive at Atlanta, we will discover a new input, which is Washington, and we dequeue Atlanta. So the rest is only Washington until the end. Until the end, it means that it's there is no more when we check Washington, and there is no more value. It means that all city has been visited or searched. So that's why in this case, I use Q. Well, for the best practice also for BFS. Therefore, in here, this is I explained about the general BFS, not for, particularly for this for solving this problem. But by understanding the general form of BFS, you will I think it make you easier to understand and to use it. So I think class we have this is class graph, NTV. Well, this is in object-oriented programming format. We have this if okay, we keep it this one. This one is well, this is the edge. This is the graph. There is a vertex and adjacent, which consists of list. And then for graph, for this one is visited. As you remember that we have to flag whenever it has been visited. It's important. By default, we first we put it as false all for all. Then we start with Q. If it has already visited, then Q push back. Actually, okay. Actually, it's a little bit different. So whenever it's visited, we put it in the queue. visit through, well, it's possible also. So in this case, as you remember previously, I explained the technique is marked only after it's the queue. So if we consider this source code, it will be marked city as having been visited before it is put into the queue. We put it as true, then we put it in the queue. And this is list integer iterator E. This is vector, so it's dynamic. Then we start with queue front. We start with the queue, this one. We put where this one. We start to, maybe we start with Austin or Dallas. In this case, normally it's Dallas because Austin is the starting point. We start with Dallas, and then this one is we print out and then pop front. We pop once it's already mentioned or visited. Then for the next, we see in the adjacency list of this list. For example, as you can see Dallas over here, the adjacency list, it has Chicago and Denver. So we put inside the queue and we set it as true. That's why over here we have Denver, Chicago, and Denver put over here, and we set it as true. And that's all. Actually, that's all. After that, it's pop front, something like this. We continue this one. Houston, we check it whether it has a relation. Oh, okay, Houston has Atlanta. We put over here at the Lillian. Well, this is the problem for general problem of BFS. After that, what is important in this thing is maybe, well, it's up to you. Maybe if you want to put something like this, actually what you need is you have to modify this one. What is at edge? So we put over here 0 and 1. So maybe you can, well, I think it's, you can do something like this. For example, this one 0, you put it as the adjacency list, this one and this one. So you select between these 4 and you select, you put it as the queue. Select again, do it again. By doing this, you will find at the end, you will find like this approach and can solve it. That's why in my code, actually, this one, as you can see, set in 4, left, right, up, down. Nice, put this one. For plus A plus B for the position. Okay, I think, is it clear, Rosa? Or it's still not clear? Rosa, is it clear for you? Or others, maybe? Well, actually, maybe for theoretically, it's easy to understand, but yes, theoretically it's easy to understand, but for the practical understanding or maybe for coding, it's a little bit complicated. Actually, well, normally you have finished this BFS in data structure, but maybe you forgot about it. Well, it's normal. It's been a long time. Maybe. So okay, I think there is no specific solution. It's what we call it, like it's greedy. We can use, well, we can say it like Jigsaw, but it's unweighted. So it's more like complete search. We do it one by one over here, until you reach the end. You reach what is reaching the end? It means that you reach the whether in the minimum. Over here I declared something like this. it's 0, the x, whether the x is 0, so it will be like this. Yes, x0, sorry, x0 is over here, or x m minus 1 minus m minus 1, it means that's over here, or y is 0 over here, or y minus 1 over here. So whenever I reach a point or well, a block which arrive in here and it's not a wall, then it means you solve the problem. Okay, I think that's all for this problem, because we have limited time. Well, I can continue. Is there any further question maybe? No? Okay, I hope it's clear for you. Well, the most important is to understand how to solve it, and maybe you can use it later for the BFS. So then we start with the next approach, which is depth first search. Depth first search is undirected graph. G is like wandering a labyrinth with a string and a can of paint. So you do the vertically. So we start with vertex S, tying the end of our string to the point painting as visited or discovered. For example, this one, as you can see, we start with this one. Then actually it's up to you whether you want to go over here or you go over here. But once you go over here, you have to continue this one. In this case, it goes over here, right maybe. And then 2, and then visiting this one, that's why it's 3. Actually 0, 1, 2, 3, it's in the order. Then what happened when we arrive this one? This is what we call backtracking. So we backtrack into the previous node. So we visit, maybe we check 2, and then we check if there is any other child. No. Then we backtrack again to 1. This one is easier to implement using in my short experience, easier to implement using recursive. As you can see, maybe if you remember my previous courses about dynamic programming, solving dynamic programming, there is a solution which use complete search backtracking. It has similar approach like this, backtrack. So we arrive this one. Oh, it has another child. So we visit this one. That's why it's 4. Then actually you can choose this one or this one, but it has been already flagged as as visited. So you go directly to this one. That's why it's the order of 5. Sorry, this one. And then directly this one, 6, and then 7. And at the end, you do the backtrack again, reverse. So you do return this one, and return this one, return this one, return this one, and return this one. That's why at the end, plus H over here. It's depth first search. And if I want to, maybe at the end, it would be something like this. Maybe I'll delete this. Well, make this one. Put it as white. Color it. As you can see, because we don't use this edge, so for the depth DFS, no, depth first 3, we didn't consider it also. Something like this. As you can see, it's the first 3. At the end, for traverse, it will be the form will be in a tree. And this is the example. Well, in the contrary of BFS, in DFS it use stack. What do I mean when it applies stack? It means that we visit Austin. We start with Austin, and then we pop out. Let's see over here. We start with Dallas. Well, it has Dallas and Houston. Then this is considering the weight. So because Houston is we put it at top. So we visit maybe Dallas. Wait, let me do the example with this one, and let us create. Suppose you have a graph something like this, and what I'm to do is I want to apply a stack with DFS. So we have A, for example. So we pop out. We pop A. We have C and D. We select only one, so we select D. We pop D. Then let me wait. With this one. So we have this one, and then we visit this one. D. We pop out because it's stack. It's last in, first out. So what do we have over here? We have E. Okay. Then we visit it again. So in this case, we keep C until hit this one. C. For E, we pop out it. We pop out. Then we have whether we have F and we have G. For example, this one F and this one G. Once we visit E, as you can see, there are two child, F and G. Let's say we select the right first. So we have G. No, we select from left to right. So it means that you put F into the stack, and then we put again G into the next order. So we visit G. Okay. Since it's already pop out, and there is no further kids or further child, so we focus on the F. Then can do this. Color. Then what happened? This one from F we have what do we have? We have I. So we select I, and what do we have again? I. We pop I and we insert the H. Then we have C and H we pop out. Then we have B. That's all. And then since it's pop out, we have only C at the end. So it's quite easy with stack. As you can see, you don't need to return back over here. You just need to see your stack. What's the last index? It's right there. Or what's the last vertex? Latest vertex. And we can go there directly. So as you can see from here, we can go up directly for here. Oh, okay. So this is the last one until it's empty. So this is the purpose of using stack in DFS. And this is actually the difficulties of DFS, which is the first one is infinite recursion. If the graph may contain cycles, so our traversal problem may reach the same vertex. And the solution is similar, which is you have to mark it as true. And the second problem is the graph may not be connected. Well, this one is also from BFS. So the traversal algorithm may fail to reach all vertices from a single starting point. So in this case, what's the solution? So we list all the possible, for example, this one, disconnect. Where is disconnect? Yeah, I think this one. So we list all the vertices. Then we we solve this one. Once it's solved, we set it as, oh, this one is the value of the list stack is null. We don't exit directly, but we visit if there is any vertex, if it's not marked as true yet, then we start from there. So the marking or flagging the vertices is important. Okay. Let me check over here. Okay, I think that's all the difficulties in DFS. It's like the drawback in DFS, but we can solve it with marking. And this is some of the algorithm. We can do the put it directly, or maybe you can try to find out depth first. Search. Well, gigs for gigs. It provides good sources. As you can see, I think does it use okay, I think it's linked. It's easier than other. There is no pop out. I think they play over here about the. It's not pop out, but there's no stack over here for this one. Oh, I see. As you can see, it's just that's why it's the stack over here. It's not clearly shown. Why? Because it's used recursive. So that's why. So they consider only this one. So it's like if we consider this image, consider this one, and then once this one, we focus on this one, and then this one we focus on this one. No, this one we have. Sorry, we've generated two F and G, but we focus on this one. But once it's not, it's all visited over here, then it's return, or it can go direct because it's void. Return back over here, then starting the others. That's why it's well, it used stack, but in recursive way. In the line of is the representation of stack in the line of table is over. You mean over here, Rosa?
No, sir. The table
This one?
The table that you made before, yeah.
Yes. Yes, this is yes, it's the representation of stack. Well, actually it's only one like one column, or as you can see normally stack. How do we? Can I rotate it? No. Actually, we have to let it's stack. Actually, the representation is something like vertical like this, but I just want to show you in the horizontal way. It's easier for me.
Oh, yes.
And
Sorry.
no, it's fine. It's fine. It's good. It's good. So actually, you don't need to make this table two dimension. You only need to make it in one dimension. The important is this, and it's only the changing of the or like the evolution of the value inside the stack. Okay.
I, I, I understand. Okay.
Okay, that's
Thank
good.
you, sir.
You're welcome. So in this case, the first DFS is not clearly shown. Why? Because in here it use, as you can see, it use recursive. Then it save all the visited. It's save it over here. I think. So normally over here at edge. So the visited is focusing this one, and actually this one it from this one it generates this one and this two. Sorry, but we start with this one also. Then we return it again extra. Yeah. Well, it seems simpler. You can apply it directly. Actually, the most important is the challenge. If you apply from this mesh, is just put this one. So whenever it starts, like it gives something like this, or 0 0 over here, it means root over here. So you have to put it at edges, etc. And then it can be calculated automatically to give the result. Maybe what's the shortest path to find this one. Okay, I think that's all. Well, mainly for the DFS. My advice is at least you do the practice at least one time with BFS and one time with DFS. So by doing that, you will understand how to operate it. This is from this the course of Mr. Subakti. Let's copy paste directly over here. Well, this one is the explanation of this one. Well, even in here, there is visit all children recursively, so it's similar. And I think the code from Kicks for Kick is easier to understand. Well, for me over here, it's I did it when I create when I prepare the course of data structure. It's been a while, so I think it's just stack, so it's not in. It's up to you. You can use it this code later. Then for running time, it's similar to BFS. The number of vertex plus it's the number of vertices plus the number of edges. And this is the representation. So start 1, 2, 3, 3 and 4, because it couldn't, well, it's possible to return over here, but it's already marked. So it's block deleted, then return back to, okay, actually this one is visited again. As you can see, this is the backtrack way. Backtrack is 5, then it's over here is 6. Yes. And then return to this one, 7 and 8. Why it couldn't save arrive in here? Because as you can see, the row is in this way, from Y to from W to Y. Therefore, it's like it's not connected directly. Then, because of this, we start to see the list of the market vertex, and we found out that W is not visited yet. So we restarted from here and then go down. Well, that's the FS, and this is the DFS predecessor subgraph. It's in the forest on tree. It's the formal definition. And I think it's a further explanation about the FS, but I think the most important, try to apply it. And there is another cases of the FS edge classification, but I don't think you, well, you can just focus on applying. And this is the second problem, actually. Well, this is the same problem in Toki. This is the problem in Toki. This one, disconnected graph. Maybe I will explain it in Bahasa so that you will be easier to understand. There is a term called disconnected graph. In this problem, diberikan sebuah graf terhubung yang tidak berarah dengan N node dan E edge terhadap key node yang dipilih dari N node, yang mana node tersebut dikatakan khusus. Misalkan terdapat R edge yang dihilangkan, tugas Anda adalah menentukan banyaknya pasangan node A, B, yang mana A dan B merupakan node khusus. Dan keduanya tidak lagi terhubung. Jadi node khusus yang tidak lagi terhubung. Disconnected graph or of the specific node. Tidak ada serangkaian edge yang menghubungkan A dan B. Definisi tidak terhubung adalah tidak ada serangkaian edge yang menghubungkan A dan B setelah R edge dihilangkan. Untuk memahami, kita mulai dari sini terlebih dahulu. 2 menandakan jumlah kasusnya, studi kasusnya. Deret selanjutnya merupakan jumlah informasi penting, iterasi N, E, Q, and R. Well, N is the number of the node. E is the number of edge, which will be represented over here 4 times. Then 4 is the number of the specific nodes, so it has to be less than or equal to this one. And R is the node that has to be deleted. And here is 3. Actually, no, 3 over here is not the number of the nodes and the number of the edge that has to be deleted, but it's the order of this one. For example, 1, 2, 3. Oh, sorry. I think yes, it's correct. Number of the edge that has to be deleted. So we have nodes 4 from 1, 2, 3, 4 from 1 until N. A and B. It's the edge connecting A and B, point A, vertex A and B. As you can see, the maximum is this is between 1 until N. This case is 4, so between 1 until 4. 1, 2, 1, 4, 2, 4, 3, 4. So 1, 2, 1, 4, 2, 4, 3, 4. Connected, okay. Then the next line over here is the number of special node, not khusus. The khusus over here, well, it may be less than or equal than this one. Well, in this case, all of them made flagged as node khusus. 1, 2, 3, and 4. 1, 2, 3, and 4. And then, because this one is the number of the edges that has to be deleted, this one is 1, 2, and 3. That's the key point. Ini urutannya. Jadi 1, 2, 3 itu berarti urutan pertama yang dihapus, urutan kedua dihapus, urutan ketiga dihapus. So, urutan pertama dihapus, tadi urutan kedua dihapus, urutan ketiga dihapus. Ini urutan keempat. Dari situ, setiap kali keluarkan sebuah baris berisi bilangan menyatakan banyaknya pasangan node khusus yang tidak lagi terhubung, kombinasi. Jadi misalkan tadi node khususnya adalah 1, 2, 3, 4. Jadi ini yang tidak terhubung lagi 1, 2, 1, 4, dan 1, 3. 1, 2, 3 juga tidak terhubung, 2, 4 juga tidak terhubung. 3 dan 4 ini masih terhubung di sini, makanya tidak tulis. Nah, we have to count the total number of this combination. 1, 2, 3, 4, and 5. So that's why the result is 5. It's a little bit complicated. Actually, it's not only searching. It means not only depth first search, but I think by doing this, actually you can apply this algorithm perfectly. It means that you can do it directly. You just need to add delete edge. There's a add edge over here, and then you can add another function method called delete edge. Is it clear this problem? For the second, I think because it's only 2 nodes and simple, so there is no problem. It's 0. There is no combination. Is it clear? No, and the second, because the special dot is only 1, which is number 2. That's why it has no meaning. It's 0. Then if it's clear for you, I hope that you are able to solve it until the next weeks. Let me know if you have any problem. Well, in the WhatsApp group, you can mention me. Or maybe if you are stuck, you couldn't solve it, at least for solving this one, prepare do the presentation like explaining the problem, like previously explaining the problem and giving the explanation of representation of how you solve the problem. Maybe you can put the pseudocode or your representation or flowchart, it's up to you. Then next you calculate the source code, the screenshot of the source code and the accepted or your final status. If even it's not accepted, at least maybe you try after 5 times or 10 times, it's still not accepted. It's fine. We will still mark you. We'll stack mark your task. Okay. Is there any question? If Traversal is used, no. Okay. If there is no further question, I think that's all from me. Thank you very much for your attention. Stay safe, keep healthy. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon.
Good afternoon, sir. Thank you so much.
Thank you, sir.